Hello friends, welcome to all of you. In last class we understand that what are the important classes for the OpenFOAM, for the numerics and discretization, and for the computational domain, for the field operation, and how the OpenFOAM handles the linear equation of system. Now here we are going to understand the grid operation in the OpenFOAM. So before starting this session, we should know that OpenFOAM uses the unstructured grid. So OpenFOAM uses the unstructured grid. Okay. So using the unstructured grid, OpenFOAM handles the different geometric entities like elements, volumes, areas and centroids, as well as the phase weighting factors. Okay, so here in this series we are going to see that how OpenFOAM calculates these things. So here basically we are going to see that from the coding perspective, that how OpenFOAM calculates the volumes of different cells, how OpenFOAM calculates the areas, and finally we will see that how it will calculates the centroids and phase weighting factors. Okay, so these things we are going to see that how OpenFOAM calculates these mathematical quantities, because when we do discretization and when we do our numerical solution, so these things we should know that how these quantities, which are we call as a geometric quantities, so how OpenFOAM calculates this quantity, so that we need to know that. Okay, so let's start from first. We are going to see the area and centroid faces. Okay, so if we take one examples like this, take this is some physical problem. So we have some physical domain which is insulated at the boundary wall, and there is one T sink and there is one T microprocessor. Okay, so this is kind of a problem that you can relate with any kind of the electronic domain. Okay, so where there is some sink and there is one microprocessor. So, and if you want to do the domain discretization of this, then this would be the domain discretization. This kind of the domain discretization you can imagine. So here the points that are being connected to each other, these are called as nodes. And if you connect two nodes, then this is known as the faces, and this is if we connect multiple faces, so there will be one element. So this is kind of the 2D discretization. Similarly, you can imagine in the 3D also. So this kind of discretization is known as the structured discretization. Okay, so this kind of structured kind of the discretization is known. Okay, so generally what happens, how you can differentiate between the structured and unstructured. So in a simple way you can say that the number of faces that are creating one element is always remains same in case of the structured mesh. Okay, so if you take this element, this has around 4 faces, and if you take any kind of the elements, so all has the same number of faces. So such kind of the meshing or discretization is known as a structured. And if you take this example, so this has you can say that this is the elements and it is connected by 3 nodes. So you can count this as a 3 nodes, and these 2 nodes when connecting to each other, these are called as the face. So you can say that in this scenario the mesh is unstructured because the number of faces that are making one element always not remains the same. Okay, so there, and the like shape is also different. If you see here, the generally the faces have the same dimension, but here the face structure also changes, and also the shape changes, and also the connecting faces dimension also changes. So such kind of the meshing is, or discretization is known as the unstructured. So by default OpenFOAM follows unstructured meshing. So as I told you that OpenFOAM usually follow the unstructured mesh grading, and if we take a element in finite volume mesh in case of the OpenFOAM, so basically I mean to say that in case of the unstructured grid, so basically it is kind of a polyhedral. The type of faces of this three diagonal meshes is kind of a pentagon or triangle or quadrilateral, and that forms a shape. So that kind of shapes is known as the polygon. Okay, so basically this pentagon, triangle and quadrilateral is a type of a polygon. So you can relate like this is the 3D cells, and now here we have pointed out one faces, and here you can see that the face is the quadrilateral. Similarly, if you see this triangular kind of the mesh element, so we are taking one face here, and that face is a kind of the triangle shape. Similarly, if we have a polyhedral, so we have taken another face, so this face is kind of the pentagon. So if you want to calculate the face area of this element, so if we want to calculate the face area of this element, so we have to take the outward normal for the each faces. Okay, better way. So suppose we have one polygon shape. Okay, now suppose we want to calculate the centroid of this polygon. Okay, now there are two type of the centroid here, that is we will call as a geometric centroid, and second we will call as a centroid of the polygon. Okay, so we are talking about, so we have taken this polyhedral shape, and this polyhedral shape has a one face that is a kind of the polygon. So here we have taken the pentagon, but I think this rules will apply to the any kind of the polygon shape. Okay, now you can see that currently this polygon has around 5 nodes. Okay, and each 5 nodes will have some coordinates. Okay, so like if you are dealing with the 3D kind of the mesh, so it would have a x1, x, y and z. Okay, so it has the 3 dimension, it has also 3 dimension, and it has also 3 coordinates. Basically I want to say the 3 coordinates. Okay, now if you want to calculate the geometric central, okay, so geometric central we denotes with the xg. Okay, so basically there is a simple formula that we will divide with the number of points, that is here in case of this pentagon there is 5 number of points, and then we have to take the coordinates of each point, and we have take the summation of these coordinates. Okay, and this I will be number of the total points. Okay, so this is going to give us the geometric center. Okay, now this centroid of the polygon will be little bit different. Okay, once you find this xg, Okay, so suppose this is our XC. Now we can connect each points with this XC. Okay, so this will form one triangular shape, this will form another triangular shape, this will form another triangular shape. So for this pentagon there would be around total of 5 triangles. Okay, so we can consider it as we can say that these are the subtriangle. Okay, now since we have subtriangle, so we can calculate the centroid of this subtriangles also. So suppose we have this would be somewhere that we can calculate the centroid of the subtriangles. Okay, now for a triangle type of shape, generally this geometric centroid and the centroid of the polygon always remains the same. Okay, so for let me write. So for triangle polygon, this geometric centroid is generally also equal to the centroid of the triangle. Okay, so this that is why we don't have to worry about the other centroid of this triangle shape. So each triangle have only one centroid, in that either we can call it as a geometric centroid, or we can call it as a centroid of the triangle. Okay, so for each triangle we have to calculate the surface area, and since all these triangles are on the same face, so all the triangles have the same outward direction of the faces. Okay, so we don't have to worry about the direction at this stage. Okay, now we can calculate the like we already know that if we have the coordinates of the triangles, then we can calculate the surface area. Okay, so let's say that for this triangle the surface area is ST. Okay, so for this triangle the surface area is ST. So to calculate the centroid centroid of the polygon, this is the geometric centroid. So to calculate the centroid of the polygon, we have to sum all the surface area of the triangles. Okay, so suppose there are n number of the triangles, so we have to take the total sum of the surface area of all the triangles. Now you should remember that whenever I am writing this ST, so I am already considering the direction that is the outward to the face. Okay, so that this total surface area of all the triangles, I can take it as a SF. Okay, so now we have calculated this total surface area. So what we can do, we can to calculate our centroid of this polygon. Okay, so this is the centroid of the polygon. So here I can write the T because I'm talking about a simple triangle here. So to calculate the centroid of this whole polygon, what we can do, we can take this surface area of each triangle and we can multiply it with this centroid that we have calculated for the each subtriangle. So this is the XCE and comma T. Okay, so basically this is the surface area of the each triangle, and this is the centroid of each subtriangle. And as we already see that for a triangle, the geometric and centroid of the triangle polygon is always same. So we can multiply this XC of the triangle multiply by ST, and then we have sum over the all the number of the triangles, and then we have divide with the SF. Okay, where SF is the total summation of the surface area of all the triangles. Okay, so this formula is going to give us the centroid of the polygon. Okay, so this is the geometric center. This is a geometric centroid, and this is a centroid of the given polygon. So up to this point we have calculated the face area of this faces and that centroid of this polygon, okay, which is the face. So I mean to say that for each type of the cells we are able to calculate the surface area. For each of the face we are able to calculate the surface area and also the centroid of these polygons. Now if we take this as an element in 3 dimensions, then we have to calculate the volume. Okay, and the next task is the centroid of this element. Okay, so let's take one polygon shape, and the same logic will be applied to the all kind of the elements here. Okay, so we have to calculate the value and centroid of 3D element. Now our task is to calculate the volume of these elements and also the centroid of the 3D elements. So ultimately, as we know that we have different number of the faces, at the first level we can calculate the geometric centroid of this element. So just we have to divide with the coordinates of each nodes, and we can take the sum from I to k. So then we have to divide with the k. Okay, so if it's a 3D geometry, then we have this x, I, j coordinates. Now if we take this xg as the centroid, geometric centroid, then we can connect the faces like this with this geometric centroid, and we will able to form a pyramid kind of the shape. Okay, so you can see that this is the geometric centroid, and we have just connected each faces with this centroid. So this will give us a kind of the pyramid shapes. Okay, so I think you can understand here. Now this pyramid shape has this surface area we have already calculated here, and once we have calculated this base area, so this we can take as the base, and this base area we can take as the SF. Okay, so to calculate the volume of this pyramid, we have formula equal to the, so for any pyramid we can have a formula equal to the 1 multiplied by 3 into the base area. So we have this base area, and then there is a perpendicular height. So from the base area to this apex, that is the point G, we should have a perpendicular height. For this given pyramid, we have two important quantity, that is the apex centroid, that is the xg, and there is a base centroid, that is the xce. Okay, so we already know that how we can calculate the centroid of this base polygon, that I am calling it as a XCE, okay, of the face. So this is a geometrical concept that always the centroid of this polygon is going to lie on the line connecting apex to the base. Okay, there is also one geometrical concept that the centroid lies at the 1/4 distance from the base. Okay, so that you can just go through any elementary level geometrical mathematics, so that for any triangle, for any pyramid, the centroid lies on the perpendicular height connecting from this apex to base, and also it lies on 1/4 distance from the base. Okay, so this distance should be the 1/4. Okay, or we can also say that it lies 3/4 height, 3/4 height from the apex. Okay, so from this G there should be distance of the 3/4, and from this location there should be distance by the 1/4. Okay, so if we want to calculate the XC of the centroid, so the XC, that is the centroid of the pyramid, okay, so since we are considering the distance here, so if we transfer this concept of what x/4 distance from the base of this polygon and 3/4 from the apex, and if you convert into the coordinates, okay, then this mathematical formula of the XE of the pyramid will become like 0.75, that is the 3/4 of the XCE of the surface. Okay, and 0.25 of the XG of the pyramid. Okay, so this XG pyramid is just the coordinates of this G, and this is the coordinates of the centroid of this base surface. Okay, so that is how you can calculate the centroid of this. That is how you can calculate the centroid of this pyramid. Okay, so we have centroid of this pyramid. Similarly, we can calculate the centroid of each pyramid. Now if we want to calculate the total volume, so if we want to calculate the total volume of this cell, so that we can write it as a, so suppose if we are taking it as a V1, so similarly we can take as a V1, V2, or n, suppose there are k number of the pyramids formed due to the different polygons in this element, so we can write it as a I equal to the 1 to k, and then this is the Vi, where Vi is the surface area, volume of the each pyramid. Okay, now we have calculated the centroid of the pyramid, this centroid of this each polygon. Now if you want to calculate the centroid of the whole cell, so similarly like we have applied here that the centroid of the each triangle into the multiplied with the surface area of this triangle and then total surface area. So similarly we can do this. So XC of the cell equal to the summation of XCE of the pyramid. Okay, and similarly this volume of the pyramid, so that we are calculating using this formula. This is the volume of the pyramid, and then we can take the summation from I equal to the 1 to the, suppose there are n number of the polygons formed in this element. Okay, so then we can take this I equal to 1 to n, and then we can divide with this total volume. Okay, so that we have calculated the volume of the each polygon, and then we have taken the sum of all the volumes. So then we can divide with the v. So this is going to give the centroid of this polygon. So for that purpose, let me open the OpenFOAM. So this is OpenFOAM where I have installed. So let's see the version 2306. I think there might be some differences with your version, but the logic that we are going to see here, that I think it will work in the all kind of the version. So for understanding how OpenFOAM calculates the area and centroid of the faces, okay, so within OpenFOAM you can go inside the SRC, and then again you have to go within the OpenFOAM. Now after that there is file that you are going to find, that is the meshes, and within the meshes you are going to find one folder with the primitive mesh. Okay, so now it may depend that within your OpenFOAM version, so this is a little bit different from this coding. So we have to just go and find that this primitive mesh face centers and areas, and there will be another files that you are going to find, primitive mesh cell centers and volume.c. So these two folder is related to the cell centers and volumes and areas. So first let's see, okay, face center and areas. Okay, so here you can see that there are different member functions are given here, but we are interested in this member function, that there is a primitive tools. So like this this calculate face center and area, it is calling one member function which is from this class, that is the primitive mesh tools. Okay, so this is some function which is being called from this primitive mesh tools. So if you go here, and you can see that this .h folder is being like called here. Okay, so to understand the logic here, we have to go within this primitive mesh tools.h. Okay, now in some of the version of the OpenFOAM, okay, this definition that make face center and area, you can find the definition within this .c folder itself. In other versions, you are going to see the definition of this make face centers and area within this primitive tools.h. So let's go to, so if you go here inside the primitive mesh shape, so there is two folder, that is a primitive mesh tools.h and primitive mesh tools.c. As you already know that there is a function declaration or variable declaration is done within the .h, but inside the .c, this logic that how this function should works. So this is definition that you are going to find, that it has there are 4 variables that is being called here. Okay, in the definition, like here you can see that the list of all the faces is being called here. Okay, so whatever the faces related to meshes are there, all the faces are being called here. Okay, now after that you are going to find out the all the point field. Okay, so this is pointer which is reference to the point fields. So what are the different points are there within the OpenFOAM, so that you can find within the poly mesh folder that is being called here. And then here one pointer for the face centers, and there is one pointer for the face areas. Now if you go come at the definition, function definition, so here you can see that first we are calculating the size of function centers and function areas. So these are the two values, two variables that we are declaring with the size of the face size. Now when you go here, so here the loop is going for all the faces, whatever the size of the faces are there. So it is going to face toward the, it is going to loop for the each faces. Okay, so it starts from here. So like if we have like 36 faces, so it is going to iterate to the all the 36 faces. Okay, and for the each faces, so see this loop that we are talking about. So first it will passing the argument, that is the total number of faces is the 12, and whatever the number of creating this faces is here. Okay, so this is the number of point field that is being passed here. So this is kind of a vector quantity. So like it has also x coordinates and y coordinates and z coordinates for the all the points here. Okay, so that is why it is treated as a point field. Okay, now this loop is going to iterate for the all the 12 faces cleared here. So all the 12 faces, for all the 12 faces, this is going to work here. Okay, for each of the 12 faces, this loop is going to iterate. Okay, now first it is going to check that whether the number of points on the each faces is equal to the 3 faces that we are seeing here. If the number of points to create this face is around 3, then as we see that the treatment is very simple. Okay, that it is a triangle, and in that situation the geometric center and that centroid always remains same. Okay, and the formula for calculating the area, surface area of that triangle polygon is similarly the formula that we study. So this formula is simply applied for the triangles. Okay, so that is why you can see that if the number of points connecting that face is around 3, then this is going to apply. So first we are taking the sum of these 3 points, and then we are dividing by 1 by 3. Okay, so just by referring to this definition, you can just find out what is written here. Okay, so just you can visit to this location and you can find the definition here. So the definition you can find at this location, and this is just like 11th or 12th mathematics class that you understand it how to calculate area of a given triangle. Now let's see that if the face has not the 3 points, then what we will do. Okay, so in that scenario, okay, first we will try to decompose that face into the triangles. First we are trying to decompose the different faces into the triangle. Okay, and how we are going to do that? We have to first find out the geometric center of this face. Okay, so once we will find the geometric center of this whole the face, then using that point we will create different triangles, and with these different triangles we can calculate the sub centroid of these triangles. Okay, so let's see that how this logic is applied within the OpenFOAM. So we have first created the subnormal, so equal to the 0. So we are taking one variable which is the sum normal equal to the 0 vector, and this is sum of the area which is kind of a scalar, and this is also a vector which is kind of a 0 vector. Okay, now we are assuming that our first point of this given face is kind of the face center. Okay, so we just start with these assumptions, and we just like take the sum of all the faces. Okay, and just basically we have divided the total number of the points. So basically what we are doing here, we are just applying this logic here. Okay, so we have for this complete faces points, for each of the points we have just sum up, and then we have divided with the total number of points. Okay, so this will give us the geometric center of this face. So this is the geometric center of the face here. Now starting from here, what we are going to do, basically we are creating the triangles with the each point. So suppose this is our first point, this is our second point, this is our third point. Okay, this is 4 point and this is 5 point. Okay, so what we have to do, we have to just iterate from starting point to the last point, and in each of the 3 consecutive points we are including one as a center here. Okay, so basically what I mean to see that we are just taking, this is the, suppose this is the first point, then we are taking the second point, that is the 2, and then there is the F center. So this is going to create one triangle. Similarly, then we will go with the 2. So this is 2, and the next point is the 3, and this is going to the FC. So this is going to give us the third triangle. Okay, similarly we will do with this also. So it starts from the 3, then it will take the 4th points, and then we will take the FC, that is the geometric center. And this logic we are applying here. So starting for all the number of points, so this loop we have applied for all the number of points, since it is starting from the 0. That is why we are iterating up to the less than 1 number of points. Okay, because we are starting from the 0, and you can see that we are taking this point and the next point. Okay, and then by summing of these 3 points, we are calculating the centroid of this triangle. Okay, so we are calculating the centroid of this triangle, and for a given triangle, this geometric centroid and the centroid both are the same thing. Okay, so this is going to give the centroid of the given triangle. Now here we are calculating the area normal again. Okay, so similarly, like that formula we have applied here, similarly we are same formula, like here you can also, if you visit this formula here, then you are going to find out this is the same kind of the formulation is done here. So here we are taking the vector product. Okay, so this is going to give one vector, and this is going to give us one vector. So we are taking the vector products here, and here we are calculating the area normal. Okay, so then here we have just sum up the normal vector. Here we have calculated the sum of the scalar quantity of the area normal, and then here we have done this multiplication A star into the C. Okay, now in the area normal, generally we divide here by 1 by 2. So that is why this multiplication will done later, and even to calculate the center we have always divide 1 by 3, because we are taking sum of these 3 points 1, 2, 3. So we have to divide by the 3, so to calculate the average. Okay, so that we will do later. Okay, so here you can see that first point, second point, and third point just just addition is done, but we are supposed to divide by 3 here, and here also we have taken the vector product, but we are supposed to again multiply by 1 by 2. Okay, which is the general standard formula for the calculating the area of the triangle. So this is done later. Okay, Now this quantities, okay, so let me open. So this quantity that basically we are trying to calculate, okay, so that we are taking XE multiplied by SC for the all the triangles, and then we are trying to divide by the total area of the polygon face, and that is going to give us the centroid of the given triangle. Okay, so basically if you see that this is, so let me, okay, so basically A star into the C means A multiplied by C is the XE multiplied by S total. Okay, so that is the surface area normal into the this center point of the all the triangles, and then to find out the like centroid of the given face, we will finally divide with the total surface area. So basically this is A star into the C by sum of A. Okay, so that we are doing here to calculate the centroid of the given face. Okay, now we have already calculated the area normal here, but as I suggested you that we have to multiply with the 1 by 2 here, so that is why we are applying here by 1 by 2. Now here we are not multiplying by 1 by 2 because this 1 by 2 is also multiply within the sum AC and this sum A. Okay, here this you will find that it is written that sum A is less than root Vs is small. So this is just to avoid if some faces has zero area faces. So now let's understand that how OpenFOAM calculates the cell center and volume. So if we revise what we have done here, so now we have idea about how the face center of this different various faces are being calculated. So using those face centers, we have find out the geometric centroid of this given cell. So this is the formula that we are applying. Now using this geometric center, we can calculate the pyramid here, so like that, and using this pyramid we can calculate the volume of this pyramid equal to the 1 by 3 into the base area of the face multiplied by the distance between this geometric center to the face center. So this will give us the volume of this pyramid. Now this is the formula that we have applied to calculate the centroid of this pyramid. So that is like 0.75 the coordinates of this centroid of the face, and 0.25 the coordinates of this apex, that is the geometric center. So this formula we can apply to calculate the centroid of this pyramid. Now to calculate the centroid of overall cell, we can apply again this XE multiplied by this volume of each pyramid. So basically the XE of this pyramid, okay, so whatever the pyramid has the XE, that we will find out from here, then we will multiply by the volume of this pyramid, and this summation of volume of pyramid is going to give us this total volume, and that total volume we are going to divide here, so that is going to give us the XE here. So this complete formulation we are going to apply. Okay, so here you can see that this is where we have discussed the make this center and areas. Now here we have another function, that is the make cell centers and volume. Okay, so here you can see that we have this argument, that is the mesh face center and face area. So this face center and face area is calculated from the last function definition. Now here we have like these two value we have to calculate, that is the cell center and cell value. Okay, so that is why this two argument is also defined here. Okay, now if you come here, so these are just the like copy and creating the reference of the function. Okay, so now the most important thing is this function here. Okay, so here you can see that we are doing this function definition for the 2 times. Okay, for owner faces we have one for loop, and for neighbor faces we have one for loop. So OpenFOAM, like to avoid the redundancy of this LDU matrix that we have discussed in our last class. So OpenFOAM treats the faces in this owner form and this neighbor form. Okay, now that we are going to see that why this OpenFOAM do that and how this OpenFOAM do that we will see in the future classes. But here you can understand that just we are looping through all the faces. Okay, so for a given cell we have neighbor cells and we have owner cells. So for a given cells we are just calculating summing up the cell centers of the each faces, and here we are calculating the number of cells within a given face. Okay, so using the owner faces and using the owner neighbor faces, we are just calculating the cell centers of each the faces, and then here we are just dividing all the face center by the total number of face centers. So this is for each cell we are just dividing the cell center for each faces, and then we are dividing the number of faces. Okay, so this is going to give us the geometric center of all the cells. Okay, so till here we have the geometric center of all the cells, all the faces. Okay, and now from here we are going to use the formula. So if you see here, we have doing this face area, then this is the basically a dot product here. Okay, so basically here we are taking the dot product between the base area into the perpendicular height. So this height is calculated from this geometric center and this face center. Okay, so using that value we have this face area, and then we are taking this FC minus this is the face center. Okay, so then we are taking the dot product. Again we are not dividing 1 by 3 here, we will do this divide by 1 by 3. So like here we have 1 by 3 multiplied by base area into the this height. So this division we are going to do at the last. Now here we are calculating the center of the pyramid. Okay, so this again same formula, like 1 by 4 into the cell center of the face, and to the 3 by 4 into the FC. Okay, so 3 by 4 into the face center and 1 by 4 into the geometric center. Okay, so this formula that I have given here, that we are using to calculate the cells center of the each pyramid here. Okay, now we have to calculate the total value. Okay, so that we are doing here. So we are just using this formula, we are just summing of all the volume of the pyramids. So that is going to give you the, so that is going to, so this is one pyramid, so there will be a number of pyramids here. So just if we sum up, so we will have a total cell volume of a given cell. Okay, so this is for all the owner faces, and similarly there will be for all the neighbor faces. So to calculate the cell center, we are again applying this formula. So that is the centroid are the pyramids multiplied with the volume of the pyramids and then total value. Okay, so if you see here, so that basically we are applying here this volume of the pyramid multiplied with that center of the pyramid that we have calculated here. Okay, so then we are keeping this, and then finally we are here dividing with the cell center by cell value. Okay, so this cell center by cell value. So cell center we have already multiplied here with this centroid. So this is going to give us the cell center of each of the cells here. Now here to get the cell values, we are dividing by the 1 by 3. Okay, so here I am taking one exercise, and that we are going to do here. Okay, so that exercise, I think this video is already long, so I'm just writing here the exercise, and maybe I will give a short video on this exercise. Okay, and remember here that I am just following the Mockle textbook to create this content. So if you feel to know more about these things, you can just refer that book. So this exercise I am also taking from that book only, and in that book there is no solution for this exercise. So I'm going to provide you the solution in the next video. Exercise is that you write a program that reads OpenFOAM. So first you have to write a program that is going to read the OpenFOAM, and then again checks that for each element of the surface vector is 0. Okay, so this you have to write a program for that, how you can do, but I am going to give you solution in the next video. So you can just start creating an object for the mesh, and then after that you have to of course this primitive mesh tools. So you just try to import this in your .c file, and there will be one function is given here in this primitiveMesh tool.h. So in this primitiveMesh tool.h there is one function that you have to find out that which function you are going to use and how you are going to use. And using that function you can check that for each element of the surface whether the vector is 0 or not. Okay, so you have to count the number of elements who has the surface vector is 0, and then you have to print. So I hope this video is a lot for you, and I will continue this series, and in next session we are going to see more depth knowledge about the meshing from the perspective of these neighbors and that owner that we have discussed a short in the current video. Okay, so thank you for watching this video.